And we're live.
So mark your own name. Oh, my favorite student of all time. You know, what would be strange is if I ever had a kid that was named that. She'd be like, "You're creepy, Mr. Yeah, okay. Anyways. You know what? You're going to put your phones away, and you're going to probably get out your pink sheet and your green sheet, because you want both of those for the test. If you don't have a green sheet, I got extras. If you don't have a pink sheet, try and share with somebody. I got a couple of extras, but not that many extras. It says, circle the letter of the best answer. You may refer to a periodic table, an ion chart, and the reference sheets. Which of the following is true of subatomic particles in a nucleus of vanadium-50? So let's come back. Here is the mass of vanadium-50, except I'm going to use a mass of 51. So it has a mass of 51. That does not tell me, that has nothing to do with exactly the number of protons or neutrons or electrons. It tells me the grand total number of protons and neutrons. It doesn't tell me how many electrons, because you know how much electrons weigh? Pretty much nothing. So this number here tells me its atomic number, and in a wonderful coincidence, Amber, that tells me the number of protons. So the first thing that I would say is it has 23 protons, 23 protons. It doesn't have 27. It doesn't have 27. C and D are wrong. It could be A and B. How many neutrons? Well, to find the number of neutrons, that's going to be the mass minus the number of protons. And this is why I said you might want to bring a calculator. Now, some of you can do this in your head. 51 take away 23 is 51 take away 20 is 31 take away 3. 28 neutrons. So that's wrong. The answer is B. I'm definitely going to give you some kind of an isotope, some kind of a mass, and say, hey, how many neutrons or how many protons? Oh, how many electrons are there? Assuming this is neutral, the same as the number of protons, 23. Otherwise, it's an ion, and it didn't say anything about this being an ion. Why am I wrong? Why are we wrong? So what mass did I circle here? 51. But what isotope did they tell me this was? What mass did they tell me this was? Okay, they said this has a mass of 50. So I said it's got a mass of 51. That's what the average atom has. But they gave me, Laura, here a specific isotope. So you want to read these questions very, very carefully. They said this has a mass of 50, which means it still has 23 protons. Oh, no, does it have 23 protons? Yeah, it still has 23 protons because that's the atomic number, but it does not have 28 neutrons. Actually, how many neutrons does it have? So the correct answer is not B. The correct answer is A. That's the difference between what's on your chart, the pink sheet, which gives you the average masses, and if I give you a specific isotope, if I give you an atom dash a number, use that number, Alon, as your mass. I don't care what the pink sheet says. Okay? So doing that mistake on purpose reinforced what not to do, I hope. Kenzie, you got this quiz?
Yeah.
Good. Number 2, which of the following nuclear decay equations represents alpha decay? So on your green sheet, it tells you that alpha has the symbol like that, has a mass of 4, and a charge of 2. So what you're looking is, well, what kind of decay is this first one here? That's beta, so it's not that. How do I know it's beta decay? Because that plus 0 minus 1 beta. What's the second one? But it doesn't say alpha, it says He. We said that an alpha particle was identical to a helium nucleus, and that's on your green sheet as well. It does have both on your green sheet. It says you can write an alpha particle either one of those ways. I like the alpha symbol because it's nerdy, but helium nucleus is in some ways, in terms of the chemistry, nicer because it tells you where the heck your alpha particle probably came from. So this is alpha decay. What about the third one? Also alpha decay. What about the fourth one? Gamma. What's this little star right there? What does that mean? That tells you, that's our symbol for this is a radioactive element and it's going to give off something, but it's not going to change its mass. It's not going to change its number of neutrons. It's giving off gamma particles, which don't change the mass or the number of neutrons, but which do kill you. So the answer is 2 and 3 only, B. Is that okay, Sarah? I hope. Number 3 says, consider the following partly completed nuclear decay equation. I'm going to give you some nuclear decay equations to complete, to fill in the blanks. How do you fill in the blanks? The top has to balance. So how much mass are we starting out with at the very beginning here, Dylan, my friend? How much mass must I have at the end then? 14. So if this has a mass of 0, this better have a mass of 14, which means B has to be wrong. It's got a mass of 10. Also, the number of protons, the charge has to balance. I'm starting out, Amber, with a charge of what? 6. How much must I have at the end? Well, I must have 6 grand total, and you're right. If that's a -1, this has to be a 7. And that atomic number is also going to tell you what element we're talking about. What is element number 7? Nitrogen. So this nuclear decay equation, carbon-14, decays into a beta particle and nitrogen. D. D. This is what they can use to do carbon-14 dating, by the way. Turn the page. Number 4 says, refer to the common isotopes pairs chart. Let's go find that, Mr. Dewick. Science 10, radiation, whoop, details, let's do that. Where's my reference sheet, Mr. Dewick? I got it on here somewhere. Radioactivity data sheet. So here is my common isotopes pairs chart. Carbon-14 decays into nitrogen-14 in 5,730 years. Half of it decays then. So now let's answer the question. What's the maximum effective dating range for carbon-14 dating? What's the half-life of carbon-14? What does it say on your green chart there? What's the half-life of carbon-14? 5,730 years, which means it's not useful to try and figure out if something is only 14 years old. We can't measure that accurately. And you know what? We can do better than 1 half-life. We can even do better than 2 half-lives. Carbon-14 dating is pretty good to about 50,000 years, about 10 half-lives. Well, about 8 half-lives, if I'm really going to be fussy. If something's older than that, we need to look at a different element and a different half-life to try and figure out how much of it is left. Number 5 says, refer to the common isotope, this thing, to determine the age of a sample of rock that contains equal amounts of uranium-235 and lead-207. So uranium-235 decays into lead-207. When will you have equal amounts? When half of the uranium has become lead, when 1 half-life has occurred. How long will that take? 710 million years. Yep. B, 710 million years. Number 6, potassium-40 is a radioactive isotope with a half-life of 1.3 billion years. I'm probably going to use that. It has the daughter argon-40, so potassium turns into argon. How old is a rock that is found to contain 1 gram of potassium and 3 grams of argon? How much rock is there grand total? How many grams grand total? 4 grams. How much is potassium? As a ratio, we would say that 1/4 is left. Is that okay? How many half-lives is that? Well, if I start out with 100% or 1, and I go 1 half-life, divide by 2, I have 0.5 left. If I go another half-life, I have 0.25 left, and 0.25, Darian, is 1/4 as a decimal. Is that okay? Yeah, or have I lost you? You with me? So this is really 2 half-lives. If you got 1/4 left, 1 out of 4 left, 2 half-lives. What was the half-life? 1.3 billion years. How much is 2 half-lives? 2.6 billion years. Okay. There's going to be a few half-life questions on your written section. In fact, in a little bit, I'm going to give you another take-home quiz, and that's going to have some practice half-life questions. They're tricky. They are tricky. Number 7. Which nuclear symbol correctly completes the following nuclear equation? Okay, this is fission, it looks like. We're firing a neutron into uranium and splitting it up. Once again, Kinsey, we want the top numbers all to balance. So, what's the mass of this one, Kenzie? Can you read it right from there?
235.
And what's the mass of a neutron?
1.
So I start out with grand total 236 worth of mass. How much must I have at the end? The same amount. What's the mass right here? Yep.
143.
And what's the mass of a neutron?
1.
But how many neutrons do I have? Yep, say it nice and loud. You're right.
3.
Okay, so to get the mass, we're starting out with 236. And apparently on the right-hand side, I've got 143. And I've got 3 neutrons. So if I subtract, I should be able to figure out how much mass has to be left. Yes? 236 minus 143 minus 3 neutrons. The mystery mass, the missing mass, is 90. And it turns out I'm done, but let's just see how we can get the bottom number. So how many protons do I have starting out? 92. How many protons must I have when I'm done, Justine? 92. How many am I starting out with? 92. How many would I have at the end then? 92. How many protons do I have? What's the charge that I have right there? What's the charge on a neutron? Trick question. What's the charge on a neutron? It's a trick question. 0. So I got 55. I started out with 92. I think if I go 92 take away 55, if I go 92 take away 55, I get the atomic number has to be 37. And if I look on my pink sheet, element number 37 is rubidium. So even if it wasn't multiple choice, if it was a written question, hint, 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 I could still fill in all the blanks. Yes? I hope. Turn the page. We skipped number 8. Number 9, which of the following descriptions applies to the nuclear reactions that produce energy at the core of the sun? So there's 2 types of nuclear reactions that we looked at. We looked at fission, and we looked at fusion. Fission is breaking apart, splitting the atom, creating a fissure, if you're looking for a way to remember it. And we do that all the time in nuclear reactors. Unfortunately, fission leaves lots of nuclear waste, and the nuclear waste is tough to deal with. Fusion is what goes on in the sun. That's when hydrogen atoms become compressed and turn into larger atoms. That's when atoms get compressed and become new atoms with a larger mass. So, which of the following describes the sun? Heavy, unstable nuclei split apart? Nope. That's fission. That's what we do in nuclear reactors here on the Earth. Lightweight nuclei release energy when they join to form one nucleus? Yes, that's fusion. That's what we can do in the labs right now, but not without putting in more energy than we get out. If we can figure out a way to do fusion and get more energy in than out, sorry, more energy out than in, we're laughing, because fusion has very little nuclear waste. The reaction produces products that are radioactive. No. A. B. That's what, of course, what I mean. Sheesh, Duick. B. Read my own writing. All the following are concerns connected with the use of CANDU nuclear reactors. Canada makes a nuclear reactor. It's called the CANDU. It's a very good nuclear reactor. We have about, I think, 35 or 40 of them in operation here in Canada, mostly in Ontario. Why don't we have nuclear reactors here in BC? Where do we get our electricity from? Okay, we're lucky we have these mountains and streams, hydroelectric power. In the 1940s and 50s, we dammed a bunch of rivers, which we thought was great. Electricity, Emily, for us is cheap. What did we really screw up? Yeah, our salmon runs have tanked. So when I was your age, in fact, when I was 8 years old, I remember doing a little book report in grade 3 on salmon fishing in BC, because salmon fishing was the second biggest industry in BC at the time. I doubt it's top 10 right now. In fact, I'd be surprised if it was top 20. So, yeah, but the problem is you've got to train the salmon to come back to their runs, and that's an expensive process because they'll only come back to where they've spawned from. It's not quite as simple as they thought, and even the fish ladders aren't perfect. They reduce the number of salmon that get killed, but it's not the same as a stream, sadly. So we don't have a lot of nuclear reactors here in Canada, in BC. Out east, they do. Psst. Put it away, or I'm going to hang on to it for the remainder of class. Got me? What are problems with nuclear reactors? A, the nuclear reactor might have a runaway chain reaction. Well, that's a problem, but we do have a fairly good solution. We have lots of different safeguards. We can work around that. The nuclear waste produced in the process might be stolen to produce nuclear weapons. While that's true, we can work around that by just locking nuclear waste up under tight security. The nuclear waste lasts millions of years and might leak out into the environment. That is what we're stuck with. We got no way around that. They put them into lead cement containers. They store it underground. But we're committed, Amber, to storing it for millions of years. Which, I mean, you think about how long, yeah, we're basically going to be storing it forever. The odds are it will outlast us. Radioactive isotopes might be emitted during normal operation and harm people. Again, that is true, but if we surround it with lead and concrete, we can take care of that. We have workarounds for all those three issues. That third one is the big issue. A little matching. Let's see. High energy electromagnetic radiation, I think that's A. Process involved in joining together, that's fusion. Process involved in splitting up a large nucleus into smaller fragments. Not on there. Number 11, oh, I guess I should look at the numbers. There's more letters than there are numbers. A beta particle, that's the electron. Where's the electron? Fast-moving electron that has been ejected. F, right? 11 is F. 13, mass number. The sum of the number of protons and neutrons, D. 14, daughter isotope. A newly formed nucleus produced during a nuclear reaction, I think. Is it G? I think G. Half-life, the time it takes, E. FADGB. So the answer is through 11 through 16, FADGB. Turn the page. Short answer questions. Potassium-39, potassium-40 are isotopes. How are they similar? What do they have the same of? Two things. Same number of protons, yes. And they have the same number of, one more, You're right. No, I think maybe I heard it right. Electrons. Electrons. We forget that because the electrons are so light, they have basically no mass and they don't show up in the numbers. But yeah, protons and electrons are the same. How are they different? Sarah, what do they have different of?
Neutron.
Number of neutrons. Okay? In fact, I can tell you which one's heavier. Which one is heavier, potassium 39 or potassium 40? Potassium 40. Why is it heavier by exactly 1? One extra neutron. Some half-life questions. Number 18. If 200 micrograms were present in a sample of pollen, how many grams would be left after the following periods? Now we're talking carbon-14. What's the half-life of carbon-14? 5,730. So how many half-lives is A? 1. So take 200 and either times by a half or divide by 2 once. There would be 100 grams left. How many half-lives is 14,600? I'm not sure. I'm going to go 14,600 divided by 5,760, and I find that it's 5,730, Mr. Dewick. Good gosh, do the math right. 2.5457. How many half-lives is that? Around, now I got a problem with this here. Why are they going 14,600? They should be going nice even numbers. I'm going to say nuke B. Doesn't work out evenly, and I'm only going to ask you to do ones that work out evenly. C works out evenly, though. Hayden, how many half-lives does it want me to do in part C? 4. So here's what I'm going to do. Start out with 200. Once. Twice. 3 times. 4 times. Right? Divide by 2 4 times. If you want a shortcut, you could go 200 divided by 2 to the 4th power using your exponent. Divide by 2 4 times. There is a shortcut for repeated division and multiplication. Little exponents there. Anyways, 12.5. How many years is that, by the way? Well, 5,730 times 4. That would be 22,920. So if you knew that you had 12.5 grams left, you would know that this sample was about 22,920 years old. Give or take a few hundred years. Last 3. Provide the nuclear symbol for the parent nucleus for each one. Okay. If we end up with AT and it's alpha decay, what the heck did we start out with? Well, here's what we're saying. We ended up with 207, 85 AT, and we ended up with an alpha particle. How much mass did we start out with then? 211, right? And how much charge did we start out with then? 87. What element is that? Element number 87. Francium or francium? That was the one that was so explosive when we looked at them dropping all of those ones in the column into water, and francium they couldn't even get permission to do, right? They did cesium, and that was the one that destroyed the bathtub completely. So the answer I'd be looking for 19A is that right there, B. we ended up with 239, 94 Pu plus a beta. What did we start out with? How much mass? 239. How much charge? Can you see it? How much charge? What must this have been? 95? I think I disagree.
No, it'd be 90.
Well, 93 because it's, yeah, a negative electron, right? What we're saying is a neutron split up and it sent out a beta particle, electron, and it kept an extra proton, which is why we've moved one up on the atomic table in our answer. What did we start out with? Element number 93, which is
Neptunium.
Neptunium. Named after the planet Neptune. C. Okay, we ended up with 24, 12 mg, and then it says gamma decay. Gamma is that, and it has a charge and a mass of 0. Well, how much mass must I have had? 24. How much charge must I have had? 12. You know what? I started out with magnesium. Now, if I was giving this to you as an actual nuclear equation, I would put a star there, and that's how I let you know, hey, this is radioactive. If you didn't put the star there, I wouldn't freak out, but Justice, I'm a nerd. I kind of have to. Because how could I not? Okay. So that's kind of a little summary of some of the multiple choice questions you'll be dealing with on your test on Monday. In about 10 minutes. Hang on, please. How do you know that I didn't drop the L to make the Latin prefix suffix proper? So there. Maybe I spelled it right in Latin.
Good cover, good cover.
Hey, this quiz here, I went through the written section of your test. I shortened it, I changed the numbers, but this is some of the stuff you're going to see on your test. So for the remainder of class, you're going to work on 2 things. I'm going to give you, even though I'm calling this a take-home quiz, I want you to use this time in class to really get the hang of this. This is going to be due first thing on Wednesday. So first thing on Wednesday, we're going to go through this in detail. It's got some nasty questions on here. Make sure you notice that there is a question on the very, very back page as well. If you finish that, good review is from the notes on 7.3. Here is a chapter review. I emailed you an answer key to this. This is what you're also going to work on today and Wednesday. This is going to be due the Monday of the test. So you may have some homework for the long weekend. Well, you know what? It's helping you study, so I don't feel too guilty about that. Normally I try to avoid that, but I'll live with it. I will print up an answer key for this for you in a few minutes, and I'll hand it out, because I don't think review is very good if you don't know if you're doing it right or wrong. So I tracked down an answer key. I don't know if there's any typos in the answer key. If you find typos, if you find mistakes in the answer key, first one to let me know gets a candy. That's how that works. So what are you working on for the remainder of class? The take-home quiz, and then you can work on this here, and I'll leave this up in a second. Yes, you may hustle back, but I got a couple of videos I want to show you first.